Okay, so let's look at section 1A, exercise 8, which asks us to show that for any complex number alpha, if alpha is non-zero, then there exists a unique complex number beta such that when you multiply them, you get 1. So it's asking us to show two things here. So the backwards E means that we need to show that such a beta exists. And the exclamation point there, that's my notation for indicating uniqueness. So we also need to show that beta is unique. So any number, so in common language, this phrase right here says any complex number has a unique multiplicative inverse. That's how I'd encapsulate that. So okay, thought process. Let's do our thinking in blue for now. If we take alpha to be a plus bi, then that means that, well, we want the multiplicative inverse, so the reciprocal, right? So what does that look like? So we do some messing around on our scratch paper, and then eventually you remember something from an algebra class once long ago that said that if you have something of the form 1 over 2 plus square root of 3, the way you rationalize the denominator is you multiply top and bottom by the same thing where there's a minus sign, right? That'll work here as well. So we're going to multiply top and bottom by what is actually the conjugate of alpha. Okay, so I can get rid of this. We don't need that. And then when we multiply this out, on top, I'm going to have the conjugate of alpha. And on the bottom, I'm going to get alpha times alpha conjugate gives me the magnitude squared of alpha. So I have this. Or if you want, you can think of it as scalar multiple written like this. Okay. So let's see. So with that in mind, we can go ahead and write up our proof now. So we say, okay, so let beta be equal to this thing that we just found on the previous step right here. So it's going to be a plus bi over alpha squared plus beta squared. Oh, hold on. I forgot to introduce alpha. I should have said for alpha equal to a plus bi, let beta equal alpha minus bi over alpha squared plus b squared. A squared plus b squared. There we go. Okay, that's just because the blue stuff is supposed to be my thoughts and the black stuff is supposed to be the proof as I would write it up for a homework assignment. Okay, so then if I do alpha times beta, this is going to be by our notation, a plus bi times a minus bi over a squared plus b squared. And then multiplying out across the top, we have a squared plus b squared over a squared plus b squared, and that gives us 1. So, oh, and you know what? I should have added one other detail first. So let me put this down here and say this is valid so long as alpha, as a and b are not both 0. That's important. Okay, so so that gets us existence. That's the first part. Now we have to do uniqueness. So for the uniqueness, we go back to thinking, and what do we have? Well, first off, one idea is for when you want to show that that something's unique, one way to do that is to say, suppose two different things work. So suppose beta works, and suppose that gamma works, and then we show that beta equals gamma? Well, if whenever two things have the property, that means that they're actually the same thing, then there can only be one thing with that property. So that's a way to show uniqueness. Okay, so we let alpha beta equal 1 and alpha gamma equal 1. Those will be our hypotheses. Okay, and so when I said beta works, that means it's a multiplicative inverse for alpha. And when I said gamma works, that means it's a multiplicative inverse for alpha. Okay, oh, wrong color. So let's see. So then what do we have? Well, I can look at beta, alpha, gamma. And on the one hand, I can parcel this as beta times alpha gamma by associativity, and then by our hypothesis, that's going to be 1, and I get beta. On the other hand, I can switch these around using commutativity, and by associativity, parcel the alpha with the beta, and then I get 1 times gamma equals gamma. And now, going from start to finish, I have beta equals alpha. Or sorry, gamma. Beta equals gamma. Okay, so let's write that up. So let's see. So then now suppose alpha beta equals 1 and alpha gamma equals 1. Then we have beta equals beta times 1, and that's by the multiplicative identity property of 1. And then that is beta times alpha gamma by hypotheses. Our hypothesis, we assumed that alpha gamma equals 1. And then we can rewrite this as, let's see, so alpha beta times gamma, and that's by commutativity and associativity. Oops. And let's see, so then this is going to be 1 times gamma by hypothesis again. And this time it's the hypothesis that alpha beta equals 1. So I included that in parentheses because we have a couple hypotheses, so I'm just clarifying which one. I mean, for something like this, it's pretty simple. It's kind of clear, but it's a good habit. And then that's equal to gamma by the multiplicative identity property. Okay, and that gives us a nice, tidy, straightforward proof.